Here we are in week 5 of social network analysis. This week we're going to be looking at small world networks. The concepts this week are going to be combining what we learned about random graphs, in particular Erdős-Rényi random graphs. What we found interesting about those is that those can really grow. You can get networks of millions of nodes, and yet the average shortest path, which scales just as the logarithm of the number of nodes, will then be, something on the order of 10. And that seems quite remarkable. Then we looked at some real-world networks and discovered that they had interesting community structure. That is, on a somewhat more localized scale, the structure is not random, but we haven't yet really delved into the very local structure, the structure of the network around a particular node. So what we're going to be doing this week is filling the gap. Is it possible for real-world networks to have small world properties like random networks do, and at the same time, can we recognize the interesting structure they have at the local, level? So just to outline, I'm going to start with Milgram's famous small world experiment, which established that it's a small world when you look at social networks. Then I'm going to be looking at some local structure and metrics, starting with the clustering coefficient and then delving into motif analysis. I'm going to then present some models, the very famous small world model by Watts and Strogatz that reconciles networks having clustering and at the same time having short path lengths. And then we're going to look at a few other small world models having to do with geography or having to do with hierarchical groups. And finally, we're going to look at, not just take these small world networks for granted, but say, where does this structure arise from? Why do we get small world networks? And then next week, we'll be looking at some of the consequences. What does small world structure mean for diffusion, for learning, and for coordination? So, that's still to come. Okay, on to Milgram. Stanley Milgram was a Harvard sociologist who wanted to know how many hops is it between any two individuals in the United States. So he recruited, I think he put an ad in the newspaper, individuals in Nebraska and actually in Massachusetts as well, but the Nebraskans are the more interesting set. And he gave them a task. He said, here's this stockbroker in Massachusetts. I want you to mail this pamphlet to him, but you can't do it directly. You can't just, stick it in the mail. You're supposed to mail it to someone that whom you know on a first name basis. And they're going to mail it to someone who they know on a first name basis. And we're going to see how many steps it's going to take. Back then, when he asked people how many steps they thought it would take, most of them guessed hundreds because they were thinking of their local network. Most of the people they knew were rather local. And so Massachusetts seemed awfully far away, and they just imagined it would take lots and lots of steps. That turned out to not be the case at all. The average number of steps was 6.5, and this is how the expression 6 degrees of separation was coined. This experiment was repeated in 2003 with email. And the task was very similar, but you had 18 targets instead of one target, 13 different countries, and you had far larger initial participation. So they got 60,000 participants into the experiment, 24,000 message chains, but only fewer than 400 actually made it to the target, versus Milgram had about a 20% completion rate. And here, the average shortest path, which spanned the globe, was really short. It was just 4 steps. So let's think about whether 6 or 4, we'll see how 4 is not the right number, really, how you can correct for it. Whether that's surprising. So in order to figure that out, first we need to know on average how many individuals does someone have in their network. Pohl and Cohen in 1978 did a study and estimated that the number's around 500 to 1,500 acquaintances. So let's be conservative and let's say it's 500. And let's also imagine that we're in a random network. And so your friends are just randomly chosen. So they're very unlikely to overlap with your friends. Now, if everyone has 500 friends, the average person would have how many friends of friends? Okay, so if you have 500 friends and each of them has 500 friends in turn, you would expect 250,000 friends of friends. Pretty neat, right? As long as the network is random. Now, let's extend this to friends of friends of friends. Okay, in this case, we have 500 to the third power, and that it means that once you're 3 hops out, you have 125 million friends of friends of friends, and that starts to resemble a significant portion of the US population. So the conclusion is that if networks are random, then 6 is not a surprising number at all. In fact, maybe it's a little bit on the large side. What if, on the other hand, networks were completely cliquish, right? So all of my friends' friends are my friends as well. They're not allowed to have any other friends outside of my friends. Well, in that case, what would be true? So in that case, you actually can't reach any other part of the network because you're in a complete clique and no one's allowed to have any edges outside of that clique. So you're distance 1 to anyone within the clique, but you can't reach, it's like infinite distance to anywhere else. So now the question is, this small world phenomenon, how does it arise, right? It seems very natural in a random graph, but in an entirely cliquish graph, we're not sure whether it can arise. But first, let's talk about the accuracy of the number 6 or 4, depending on which experiment you're talking about. One reason why this isn't necessarily an accurate number is that not all the chains are completed. And the question is, are shorter chains more likely to be completed than longer ones? And one consideration is, what is the attrition rate? And also, is that attrition rate uniform with respect to, whether that person is the next one in the chain from the starting person? They might approach it with greater enthusiasm because they were recruited. So the initial person was recruited, they might be interested, they might they might write the next person and say, this is such a cool experiment, try it out. But then that person may be passing on with less enthusiasm. Similarly, maybe the people further down in the chain are actually getting closer to target, so maybe they're less likely to drop the message because the goal might be near. However, neither of those turns out to be true. You have pretty stable attrition no matter which step in the chain you are. So now we can start to calculate the probability that a message gets through given a constant attrition rate. So let's say it's half probability that someone's going to pass the message versus just not do anything with it. And so if you have a chain of length 2, so 1, 2, you have only this person's in question, right? The initial sender sends for sure, otherwise there's no chain and we don't count it. And the recipient receives it, so they don't have to take any further action. So here, we're just wondering, is this person going to pass it on? So let's calculate the probability that a chain of length 2 gets through, and then a chain of length 5. So you should see that a chain of length 2 is much more likely to pass through than a chain of length 5. And so you can then go back and try and infer what the true distance distribution is. So for example, for the email experiment, their average number of hops was 4, but once they corrected and said, well, the longer chains were less likely to get through, they had an estimate of a median chain length somewhere between 5 and 7, sort of recovering that 6 degrees of separation again. A second factor in how accurate that number is that individuals actually may not be finding the shortest paths, right? So they don't know the global structure of the network. All they're doing is they're passing the message onto someone they think is more likely to know the target. And there was this nice study in 2005 that mapped out completely a network within an organization. So they had that map. And then they had those individuals. So the map was who talks to whom, right? And then they ran Milgram's experiment, which said, pass this to someone that you normally talk to. And they saw that roughly half the time, the individuals routing the message chose the next node to be on the shortest path, and half the time they goofed in a way. They didn't choose the shortest path. So even for the successful chains, they may not actually lie on the shortest path. So 6 might be an overestimate. Now, recently, there was a study done at Facebook showing that any two Facebook users are, 4.7 hops apart. And the question is, what does that really mean? If you look at these different social networking services like Facebook, like Twitter, like LinkedIn, and I would definitely recommend listening to the interview with LinkedIn because this question is addressed in there, or Google Plus, what direct and indirect benefit do you get from someone who's 1 hop away, 2 hops, 3 hops, etc.? So just something for you to think about. Next, we're going to talk about local structure. Local structure, though, is tied to the small world phenomenon in this interesting way. 2 people meet at a party. Within a minute, they're going through, who they know, and sure enough, they find that they know someone in common. Now, what they're likely to conclude is, oh, what a small world, or it's a small world after all. But what they're doing is they're closing triads. That is, they know, say, A and C know B in common, and now A and C know each other as well. So this triadic closure is sometimes also termed transitivity or clustering. And what we want to know is how much of that is going on in the network. Because social networks, for example, are highly clustered because a friend of a friend is likely to also be a friend. But in general, networks do not need necessarily have this property, and we still want to know to what extent is clustering present. One way to measure it is with the global clustering coefficient, which is going to pit the number of closed triangles against all connected triplets. So if you have a closed triangle, it actually generates 3 separate connected triplets, and hence the factor of 3 in the numerator as well. If the entire graph is one connected clique with all edges present, the clustering coefficient is 1. And if there are no triangles in the entire graph, then this global clustering coefficient is 0. And we'll see in a little bit how to evaluate values in between. However, when clustering was first calculated by Watts and Strogatz in their seminal paper, which we'll be talking about in the model section, they looked at a local clustering coefficient. That is, they calculated the clustering coefficient for each vertex, and then they averaged over all vertices in the graph. When you take the local clustering coefficient, it's as if an individual looks at all of their friends and says, out of all the possible friendships that could exist between my friends, how many are actually there. And the denominator here is going to differ by whether this is a directed network, in which case if you have n friends, the number of potential connections between them is n times n minus 1. Or if it's undirected, say frequently friendship is treated as undirected, then the number of possible pairings of your friends who could be friends with each other is n times n minus 1 divided by 2. And as I mentioned, if you want to get the clustering coefficient for the entire graph, you just average over all the nodes. So let's see how we would calculate this for one vertex I. Here it is, and it has 4 neighbors, or 4 friends. 3 of the friends all know each other, but the 4th friend they're keeping somehow hidden away. They haven't introduced him or her to the rest of their friends, and so all of those edges are absent. That 4th friend is not connected to any of the other 3 friends. So to calculate the clustering coefficient, we look at the number of neighbors, and we know that the max number of connections is n times n minus 1 over 2, in this case 6, but only 3 of the connections are present, and so the clustering coefficient is just 3 over 6, or a half. So I'd like you to try this with this vertex I, who has 3 friends. Can you calculate the clustering coefficient? Okay, hopefully you calculated the clustering coefficient as follows. You have 3 neighbors, which also means 3 potential edges, because 3 times 2 divided by 2 is 3, and 2 of these edges are actually there, giving you a clustering coefficient of 2/3. Let's look at this from the perspective of an individual tie. What does it mean for that tie to be part of one or more closed triads? Typically, when a tie is part of such triads, it tends to also be a relationship between individuals who have some sort of affinity and are likely in frequent contact. What you see actually is that if 2 individuals are close, so A and B are close and B and C are close, you don't often see that A and C have no tie at all, right? So there's something about close ties and closing triads. And you can develop, or you can just use this measure of edge embeddedness, which is going to look at the number of nodes that A and B share in common divided by the total number of neighbors with either A or B. And the higher that quantity, the more embedded the tie is. The more it's part of lots of closed triads. Now, you might say, well, I looked at my Facebook graph and some of those ties seem pretty embedded but aren't necessarily close. And I think, again, it's really important to think about what your network is. For such ties to be formed on Facebook, they may have just been, everyone at the same high school adding each other on Facebook, right? So it signifies a shared context, but not necessarily a closeness. On the other hand, if you were to filter the ties to only be individuals who regularly interact on Facebook or regularly interact in real life, and you still saw a lot of triads, you could conclude that this is really an embedded tie that's part of a closely knit clique. Just another example of this. So there was an older study that asked school children to name their first through 8th choice of friends at the school. We know how this turns out, right, from the dining tables data, dining table partners data set. But there is this interesting analysis that was then done that said, okay, let's go back to that thought experiment, right? Before we had an individual and their 500 friends and their, and 500 of each of those friends, etc. Here, They just looked at expansion by 2. And in one case, although this graphic isn't going to match, it's out of the Aral and von Alstein paper, but hopefully it illustrates the point. So when they used the 7th and 8th choice, so these weren't their closest friends, the number of people n hops out was far greater than when they used the 1st and 2nd choice. And the 1st and 2nd choice looked something like this. My best friend's friend is also likely to be my friend. But if I looked at my 7th or 8th friend and their 7th or 8th choice, I'm likely to move pretty far away. So there's this notion that it's not just, the distance, but that the strength of the tie and the embeddedness of the tie matters as well. And the question is, is it good to be embedded? Well, perhaps when you're in middle school or high school, being part of a clique is a good thing. It makes you feel secure. You have a gang that you can hang with. It's good. But as we saw in homework 3 with the Aral and Van Alstein paper, being a broker has some advantages as well. For example, the amount of novel information that you receive, or looking at Ron Burt's papers, you're more likely to be generating good ideas and to be recognized for them if you're a broker. So it really depends, right? With all network analysis, it depends. Finally, there's a study that said, strong ties, weak ties, let's not treat them as binary. We just got this awesome data set. This was J.P. Onella and his collaborators. We just got this data set that has, a huge call graph. Who called whom, when, so you can get frequency of interaction on this graph. And they looked at how things might diffuse depending on the strength of the tie. So first of all, they found a skew in the degree distribution, but they also found a skew in the strength of the tie. That is, how often two individuals communicate. Many individuals, many pairs communicate infrequently, and very few communicate extremely frequently. They also looked at the embeddedness of the tie, and I'll just do a zoom on this graph. They found that in general, there's a positive relationship between how embedded the tie is and how frequently the two individuals communicate. So it's just a validation, right? Embedded ties tend to be closer ties, at least when you're talking about phone communication. Next, they wanted to know, well, so which is it? Is it strong ties that are crucial for information diffusion because those are people you talk with often, or is it weak ties because they can go further in the network? It turned out it was neither. It was the intermediate ties, the people you talk to every so often, not too rarely, but who aren't part of your very local clique, who tended to be most instrumental for information diffusion. And they did another thing, which was to randomize the weights of the edges. So in the real world network, what you have is that the strong ties tend to be embedded, but then they just changed this, not changed, but they reassigned the strength of the tie at random to any edge in the network. And what they found, so potentially now weak ties became strong ties, etc., without changing the overall configuration of who talks to whom. And that caused information to move much more rapidly. So they did confirm that this kind of localized clustered structure is impeding network flow in a sense. No judgment about whether that's good or bad. You can do even better if you look at the directionality of the links within a closed triad or open triad, or even slightly larger structures, because that will capture more the dynamics of the interactions that are actually kind of driving the network or driving the edges within the network. So you can take a network such as this one and deconstruct it into different triads and then count, for example, how many times did you see a feed-forward loop? Well, it looks like there's one here, and it looks like there's one here again. So what does that mean? What type of a network is this? How would it compare to other networks or to random networks? So in addition to, where do we have here's the feed-forward loop, you have a number of other 3-node motifs. You kind of enumerate all possible ones. And so the feed-forward loop occurs often in neural networks, and it seems to be used to neutralize biological noise because X activates Y, activates Z, but X also directly activates Z. You can you can encounter other things. So a single input module might be found in gene control networks where X might be activating a number of other genes. You can up it to 4 nodes. Why stop at 3? Well, I'm going to tell you in a sec why you might want to do that. But here is a 4-node motif that has parallel paths, and these you might find in neural networks and in food webs. So the lion who eats the zebra and the antelope, I think that's an antelope, who are in turn each munching some greenery. And there are many more 4-node motifs than there are 3-node ones, and it's more computationally expensive to get them, but it may be worth your while if you have not a huge network to deal with. The reason why it's computationally expensive is that not only do you want to get the counts of how many times did the feed-forward loop occur, but what you'd really like to know is that unusual? I mean, so it occurred 5 times. Okay, is that high or is that low? And the way that you can figure that out is you generate the equivalent random graphs. Equivalent could mean that you just take the number of nodes and edges and you generate a bunch of Erdős-Rényi random graphs. Or you may think that some of the motifs are a result of a skewed degree distribution, in which case you want to keep the degree distribution the same. And what you can do is break the edges, so each node has the same number of edge stubs, and then rewire them at random and see, even controlling for the degree distribution, is the number of motifs that you counted unusual or not. And the way that you're specifically going to do this is you're going to calculate the z-score. So in your Erdős-Rényi random graph or equivalent random graph, you're going to get some counts, and they're going to be normally distributed for the number of times that a certain motif occurs, and then you're going to see where in this distribution your actual count lies. If it's up here, it means that it's overrepresented in your real network, and especially once you get z-scores above 2, this is what becomes statistically significant at the alpha 0.05 level, meaning that there's only 5% chance that it occurred by chance that you saw such a motif. Similarly, if you are all the way out here with a very negative z-score, it means that somehow this motif does not occur in your network as much as it would if everything was just wired randomly. You can download software, free software, that will run this analysis for you, and it has this nice output, or you can actually also use iGraph. It has, I think there it's called Triadic Census, but it's very much the same functionality. What this research group, Uri Alon's research group, did next was to show that a lot of different networks fall into these superfamilies based on a motif profile, and they designed this kind of measure that looked at the z-score for each of the individual 13 3-node motifs, and then just looked at whether the z-score follows one pattern or whether it follows another. And for example, language networks that have edges between words that occur adjacently in text, so to be or not to be. Um, that's a little fourth cycle in there. Across different languages, the motif profile is very similar. So your task is to find, based on their triad census profiles, which two kinds of networks exhibit similar structure. Hopefully what you found, actually they're plotted together, is that the World Wide Web and social networks tend to have similar frequencies of different motifs. Not to say that all web is social, but that perhaps some of the dynamics driving social networks, for example, triadic closure, friends introducing one another, may also be at work in the web, where if one page links to another, it might start copying some of its links, again, closing triads. So to understand this further, can you tell which of the following triads is underrepresented in social networks? Hopefully you've seen that it's this one, triad number 6. And this, if you remember from the beginning of the presentation, is the forbidden triad. That is, A and B have a mutual tie, and B and C have a mutual tie, but somehow A and C don't have a tie to each other. And you might imagine that poor B is really stressed out because B gets along with A and B gets along with C, but somehow A and C do not get along with each other in turn. So just to recap on motifs and clustering, so given a particular structure, you can search for it in the network. For example, you can count the complete triads, you can summarize that as a cluster coefficient, or you can create this motif profile. The advantage is that these motifs can represent certain functions or certain trends, and just you can validate by seeing whether those are present in a network, or you can discover them. Hey, this motif is very frequent in this network. Let me figure out, what is causing it. Can I understand some of the underlying dynamics, which is a real boost. So for example, if you have what you think is a good model of how your network is being generated, and then you run the motif profile on your model simulated data and you run it on your real actual network and they don't agree, it means that something's missing in your model. And the motif profile is very rich in kind of discerning these differences. One disadvantage of using motifs is that, again, it's just like with the K-cliques and K-cores. You can look for these motifs, but you may not be able to tell whether they're actually part of some sort of larger, interesting structure. So because you're looking with a microscope, you may actually miss the big picture. Okay, so far we've established two things. There is a small world phenomenon in social and other networks, and there's all this interesting local structure, which we can capture in part by measuring clustering. And this extends beyond social networks, right? That you have high clustering and short average shortest paths. For example, and you have this in neural networks, actor collaboration networks, which are admittedly social, semantic networks of languages, and networks such as food webs. The first to tie it together, how is it possible to have high clustering and low average shortest path, were Watts and Strogatz. What they said is, let's start with a regular lattice. In this lattice, every node is connected to its two closest neighbors on either side, so 4 neighbors total. And you can vary this number, of course. And we're going to start rewiring or just adding random edges. Eventually, it's going to look like an Erdős-Rényi random graph because all of the edges are going to be random. But what they wanted to know is what happens in the middle. And so I mentioned 2 ways that they can go about this. They can rewire the links. So for example, here, this node used to be connected to this one in the lattice, but now it has a random tie to a randomly chosen other node. Or you can simply just add edges on top of the existing lattice, eventually getting something that looks mostly random, but it's overlaid on the original lattice in the ring. And you just take care not to do some things, for example, rewire to yourself, or have multiple edges to the same node. So just to recap, you have this lattice. Each node has 4 nearest neighbors, and we want to distinguish, now that we can tune, what does the network look like when there's a small probability p of linking to a random node as opposed to just your neighbors on the lattice, and what happens. So for small p, we know it should look like a regular lattice. For large p, we know it should look like a random graph. So just to check your understanding, which one of these is a result of higher rewiring probability? So hopefully you can see that this one has had more rewiring happening, or actually looks like that in this algorithm the edges were just added on top. But now we're interested in what happens in between. As we vary p, is it true that you can't have small shortest paths without also having low clustering, or can you find a sweet spot? And indeed, if you vary p here, so this is 1% of the links rewired, here you have 10% of the links, you can see that even by the time you have 1% rewired, the average shortest path of the network has pretty much dropped to far below what it was in the regular lattice. On the other hand, the clustering coefficient is still pretty much at the value that it was in the lattice. So you get this in-between regime where with just a few random links, you have high clustering but low average shortest path. And then, of course, as you continue to add more and more random links, then the clustering itself falls, and the average shortest path will continue to be very low. It basically asymptotes to what it is for the random graph. And you can try this out in NetLogo. So you can set this up, and then you can vary the probability like so, and observe what happens to the clustering coefficient and the average shortest path. You can estimate how the clustering coefficient falls as a function of the rewiring probability p simply by considering that the chance that a rewiring will form a triad by accident is very slow. What's going to contribute more to the clustering coefficient is the probability that out of this triad, all 3 of these edges were preserved, which means that each one of them is going to be rewired with probability 1 minus p, so the probability that all 3 of them are intact is 1 minus p to the third. And then the clustering coefficient for this given rewiring probability is just a drop from the original lattice clustering coefficient times 1 minus p to the third. And this is what the function looks like. Here it's on linear instead of logarithmic axes. But there isn't really such an analytical derivation for average shortest paths. And here we can just look at a bunch of different networks and see how their empirical properties match up with what we expect of a small world network. So the thing to look at is these are networks of widely varying sizes. They're quite different. Film actors, co-authorship network, substrate graph in E. coli, and the C. elegans neural network. This is the actual shortest path, and this is the shortest path in the equivalent random graph. And you can see here that these values are actually quite close, if not in some cases even a bit lower. So it's not the case that because these networks have more structure that their average shortest path is significantly longer than it is for an equivalent Erdős-Rényi random graph. And then if we look at clustering, here is what it would be for the equivalent random graph. You can see rather small values, and the actual observed is much, much higher. So these are all highly clustered networks that have the small world property. So which of the following is a description matching a small world network? Just to make sure we understand what we're talking about here over and over again. What is missing, though, from the Watt-Strogatz model? It's neat that it could explain clustering coexisting with short paths, but there's much in the real world that it doesn't capture. For example, it rewires the links at random, and for most of us, our experience is that we're not just as likely to know someone across the globe, no matter what Coursera is doing at the moment to help bring us all together, than someone who maybe is in the neighboring town, right? So maybe it would make sense for the links to depend on geography. Yes, I'm much more likely to know people living on my street, but I'm also more likely to know people who live in the same city than I am to know people in a distant city. And what about hierarchical structure and groups? I mean, you can think of geography in a hierarchical way where a neighborhood is part of a city that might be part of a larger urban area that's part of a county, etc. So how is that captured? And maybe geography is not the only kind of nested structure that we're in. We're part of different organizations as well. How are those nested? And then it doesn't capture the presence of hubs, which we know to play a very important role in many networks. With the Watt-Strogatz model, for the original lattice, each node has exactly the same degree. So naturally there are no hubs, but even as you rewire, the model that you're tending to is the Erdős-Rényi random graph, which again does not have hubs. So the model doesn't really capture a lot of the real structure, but it goes a long way towards explaining what we do see. Here's a hint as to how geographic ties may be distributed. This is from the original paper by Milgram. He says, the geographic movement of the message from Nebraska to Massachusetts is striking. There's a progressive closing in on the target area as each new person is added to the chain. So it seems like the way that the message is traveling is that it makes large hops initially, and then as it gets closer, it's really homing in using short nearby ties. So how is that possible? Well, John Kleinberg proposed a model of small worlds that are laid out on a lattice, so for example in a 2D lattice. He said, in addition to these local lattice edges, you're going to have the probability of a link between, say, nodes U and V to be proportional to the distance between U and V to this exponent minus R. And the question is, what happens as this exponent varies? So I'm going to just show you briefly a NetLogo demo that I'm going to try and figure into your assignment. So here we can vary what R is, and you can set up the network. It's rather slow because you need a large lattice in order to see how the search starts to work. And then we're going to repeatedly be selecting a target and a starting point and seeing, using a greedy search, at each point, each node selects one of its neighbors who's closest to the target. How quickly does the message reach the target? And you can also vary the this probability, so we can make the links highly localized by increasing R. So let's just look at what that looks like. Hopefully you should be able to see the edges Okay, right. So almost all the edges are local, and if they do come out, they're just kind of being very, very short bridges. And so if we then do a search, you can see it going very, very gradually because it basically has to make all of these little steps. On the other hand, if we um, change it so that we allow many long-range ties, let's see what that looks like. The edges might be so far ranging that they'll obscure the lattice structure altogether. Indeed. And now we can start. And here the lattice really isn't large enough to show what's going on, but typically you see a very large initial jump and then kind of going along the lattice. And what that's showing you is that, maybe it's best if I move back to the slides. Okay, so what you should be seeing is when the edges are random, you have these long hops initially, but then there are no short range ties, so you basically have to go right to get to the target. And there are many other edges present, but none of them really took you in the right direction. Oh, sorry, I guess I'm still running NetLogo because it's being very loud. Okay, so hopefully it's going to quiet down. On the other hand, if we have this very high value of R, then what happens is that we just don't have that many long-range ties. So again, we're kind of stuck. There are ties heading in the right direction, but we're still stuck making very slow progress. And then finally, ideally for 1 over distance squared, what we have is both the presence of some long-range ties and then some shorter range ties once we're close to the target that we can use. And this is this concept of navigability. That is, does the placement of the edges allow you to, at each step, make some amount of progress towards your goal? And what Kleinberg proved was that indeed, if the exponent r is 2, that is the probability of linking to someone falls as 1 over the distance squared, then you can make enough progress at each step such that the number of steps that you have to take only grows logarithmically. So your quiz question, just to test whether you understood this, what is true about a network where the probability of a tie falls off as distance to the -2? And just a reminder, I've brought this up before, that the interesting structure that we see in social networks and other networks could really be a projection of a bipartite network. For example, if you have different contexts and individuals, and then you have individuals who share a context, have joined ties. So why not model this explicitly? So Kleinberg also proposed a hierarchical network model where you have these nested groups, and the probability that 2 individuals share an edge is proportional to a constant to the minus alpha, and then the distance that you have to go up in the hierarchy to get from one to the other. Also, if you just have these nested groups, and then you have Q being the size of the smallest group that these nodes of interest V and W belong to, then the probability of an edge existing between V and W is going to be Q to the minus alpha. So 2 different ways of representing nested group structure. such that you can now not only use it to represent geography, as I said, neighborhoods, parts of cities, parts of counties, but also other things such as individuals who are taking the same class, say at a university, who have the same major, who are in the same uh, school within the university, who are part of the same university, who are part of the universities in that country, etc. And concurrently, Watts, Dodds, and Newman proposed another hierarchical model, which is very similar, that said that the probability that I and J know each other is again proportional to e to the minus alpha x, where x is equivalent to h in the previous slide. It's the number of steps up in the hierarchy you have to go in order to join two individuals. And what was different about their work was that they looked at navigation when you have different hierarchies. So you can concurrently have a hierarchy for geography, a hierarchy for occupation, and when individuals are searching, they can switch between hierarchies. So if I know that my target lives in Massachusetts, but I also know that he's a stockbroker, well, then I can decide, oh, I know someone who's not in Massachusetts, but who's a stockbroker, or I can choose, oh, I know someone who lives in the neighboring town, even though they're not in the banking industry, I will forward the message to them. And these theoretical models then correspond closely to what was found in early experiments. There's a neat reverse small world experiment that Kilworth and Bernard did. They're the same ones who looked at the accuracy of the chains that individuals are able to create. So they gave individuals a whole slew of hypothetical targets. So they weren't actually running the chains, they were just curious, who would you pick and why? And they found that overwhelmingly people chose based on geography and occupation, so those two hierarchies make a lot of sense, and only 7% were chosen because they were hubs, because that's someone who knows a lot of other people. And also there was an absence of second degree strategy, so I'm going to pick my friend because I know they know someone in Massachusetts. So that seemed to be relatively rare. If we go back to the email experiment that was run out of Columbia, one additional nice analysis that they did was to look at successful chains versus ones that didn't quite make it. And what they found with the successful chains was that they disproportionately used weak ties, professional ties, ties originating at work or college, and those that focused on the target's work. And they disproportionately avoided using hubs, and there was no evidence of funnels. So in the original Milgram experiment, it seemed like the last people in the chain tended to be the same two, another stockbroker and maybe a tailor from the town where the stockbroker lived. But there was no evidence of funneling in this new experiment. And also people in successful chains used family and friendship ties less, and these tend to be, again, strong ties. And the strategy, interestingly, paralleled that of the Milgram experiment, which is that individuals first focused on geography, like get it to the right country, then worry about what the person's profession is, but those last few hops tended to reach the targets professionally as opposed to just trying to narrow down geographically. In this final portion, we'll see where the small world structure might arise from. Now, you can of course just assign properties to nodes such as spatial location or group membership, and then add edges accordingly. So you can have many edges between people who are in the same small group, but people who are tied only very loosely through a large group are much less likely to have an edge. However, it would be even neater if we knew, something underneath that's driving that edge formation that doesn't dictate, okay, if you're in this size group, your probability of linking is X. can we sort of derive small world networks from some sort of basic criteria that we would like to optimize in the network? So I'm going to show you two very related geographical models where we're going to place nodes on a 2D surface. So they're going to have a location, but we're going to determine who is going to link to whom based on various criteria. So one such function we may want to optimize is, you can term it energy or anything like that. We're going to have a penalty essentially for the average shortest path. So we want nodes to be a few hops away from each other. So we want to minimize the average shortest path. And at the same time, we also want to minimize the length of the edges, the actual physical length of the edges. You can imagine that you have spools of wire and the wire is copper and it costs something, right? So you want to not have wire all over the place. You want to do things efficiently. And so the average shortest path is just going to look at all distances between I and j, but in a graph sense, the graph distance. And then this other wiring distance is going to actually look at the coordinates and see how much wire did you expend wiring these together. So here's your quiz question. Given that this function incorporates two things, a person's preference for short distances and a small number of hops, let's think about two different networks. One is a road network where you're driving, and another is an airplane, or actually air transit network where you're taking a plane from city to city. So from the passenger's point of view, what would you like to optimize in an air transit network as opposed to a road network? Okay, so hopefully for the air transit network, you want to minimize the number of hops because landing and then switching planes is a very risky business, right? Because your plane might be late, you might miss your connections, etc. Versus covering long distances physically is relatively easy in a plane. So you might go from San Francisco to Atlanta only to end up in Detroit, and that's not so bad. But if you're making such a big detour driving, you'd be pretty unhappy if the road network looked like the airline transportation network. So let's look at what these networks, how they're structured if you optimize. And the method here, and I'll provide hopefully a NetLogo app that you can use to simulate this yourself, but what it's called is simulated annealing. So first you raise up the temperature, meaning that you're willing to accept configurations that are high energy. That is, maybe you have high wiring cost or lots of hops or something like that, and then you tune the energy down or actually the temperature down, and you get into lower and lower energy configurations until you hopefully find some sort of optimum. So here we have the cost of the wire becoming cheaper and cheaper, and you can see as this happens you get more and more edges that cover more and more distance, until finally you get kind of a hub configuration where every other node is connected to one node, meaning that it has a very short number of hops, right? If they're all connected to the same node, at most it's 2 hops to anywhere else in the network. But you've just spent a lot of wire. Or you may get configurations with actually multiple hubs as well. So I'll let you play with that for the assignment and see if you can get this nice hub structure. And another cute way of looking at this is you don't want to do this while you're optimizing, because of course then it's going to mess things up because your nodes now have moved and so the distance between them is no longer accurate. But you can start out with the original lattice laid out, and then kind of let the springs do their job. And so this one has a few short-range shortcuts, and you can see the network kind of coming in. And then here is that network with the big hub and several hubs. And here, I guess it's several hubs as well. So you can actually see the network kind of contracting due to these rewirings. It's making it from a large world to a relatively small world. Here is a second model with a similar idea that, again, you have some penalty for the actual Euclidean distance that you have to traverse, and then also the number of hops. And here, instead of starting with all the links from in the beginning, you're going to just apply this rule that you're going to add edges, and you're going one by one, and you're going to add the one with the smallest weight, that is this distance. So for example, if you're laying rail tracks, so how much track do you have to put down, and then what is the distance to the root node. So depending on this parameter beta, then you're going to get different types of networks. And in fact, when you put a high price on the Euclidean distance, you get something that looks more like a road network. When distance is cheap, you get something that looks more like those air transit networks that are nicely plotted in your in-flight magazine. Quiz question. A network that contains many hubs with far-reaching edges is indicative of which of these following criteria that led to the network being formed? Okay, so to recap, the world is small if you look at it as a network, yet it has lots of interesting local structure, which we can capture with a clustering. Also, we can do a deep dive, look at motif analysis. Watson-Strogatz came up with a nice, simple, small world model. Other models, though, including one created by Watts, look at other structures, geographical models and hierarchical models that say that it's not just random rewiring. The probability of an edge existing depends on the physical distance or the organizational distance between two nodes. And finally, the way that we get to this structure may be a result of some sort of optimization process. These networks are going to be used. Maybe there are transit networks, or maybe they are a result of how individuals have to communicate within the company. And so that makes actually the structure extra interesting because it tells us about the underlying needs and the underlying processes. Next week, what we're going to be doing is learning about how learning and diffusion are affected by small world and other network topologies. So I'll see you then. Okay, so here I am still at LinkedIn, and this is Matthew Bastien, who is the creator of Gephi. So the first question is, why did you do it?
It's an interesting story about my professor in 2007. We had these large web graphs, and there was really no tool to visualize such large graphs, so we just decided to create our own tool. That's the story. And then we had the Google Summer of Code that brought a lot of students and passionate computer science students to the project, and that's how it really started then and became like an open source community.
Yeah, so it seems like it really is a community in that people who use Gephi both kind of report back what the results are, but they also create plugins and other things. So what are kind of the neat either examples of applications or plugins that you think were especially like you didn't anticipate?
Yes, I mean, plugins is one of our core mission. We try to have a tool that is extensible, and that like networks are really everywhere. You can have networks of software code and networks of emails and social networks. So at the beginning, we really knew that there would be tons of other applications for not just the core of network graphs. And so we knew that people would like to extend Gephi for their particular applications and data. So that's why we created this modular architecture. And it really is interesting to see people creating like plugins to get like networks, multimodal networks, or streaming. So we had this great graph streaming plugin that was created, and you can basically see Gephi having data streamed live to it and also streamed out of it. So it became more like a platform to monitor networks, and that was really a breakthrough. And there was this great example of the Egyptian revolution that Andre Panisson recorded live when all the tweets were coming in, and he saw this network construct on real time. That was really a breakthrough for Gephi and the community.
Okay, we'll have to get a pointer to that to show the students. So I guess if it's not asking too much, how did you come to be at LinkedIn, and how has social network analysis and perhaps Gephi in particular served you in whatever you might be doing here?
Yes, so I'm a data scientist here, and we looked at graphs a lot, but that's not the main reason why I'm here. I think one of the main reasons is that when you work on graphs, and in particular in Gephi, you have a lot of interesting challenges for computer scientists. And how do you store and retrieve large graph structure? How do you visualize millions of elements on a screen? How do you create an application that can be executed on all the platforms? You learn a lot by doing this. So I learned a lot on just by coding basically, and that's how I became like more an expert in this area, and that's how they got me. So if there is any like computer science students who is interested in having some interesting coding challenges, we are having a Google Summer of Code every year now, and we are inviting students to participate and just show their skills and participate to the community.
Cool. So we'll get a pointer to that as well and share it with the students. So thanks for taking the time.
Thank you very much.
Yep.